So we are going to talk about now parallel current carrying wires. Okay, now first I'm going to remind you something about magnetic force acting on a wire inside a magnetic field. So we know that okay, first I'm going to remind you about the magnetic force acting on a wire inside a magnetic field. So assume that there's a magnetic field because of N pole and S pole of magnets, permanent magnets. These magnetic fields are fixed magnetic fields. And we know that magnetic field lines are leading from N pole and enters to S pole. Let's draw them. So magnetic field lines leading from N pole and enters to S pole. And I'm going to locate inside this magnetic field a wire perpendicularly, because when the wire is perpendicular to the magnetic field lines, maximum magnetic force acts on the wire. So magnetic fields are parallel to the plane of the board, so a wire must be perpendicular, just like this. So if you put a wire inside this magnetic field perpendicularly, maximum magnetic force acts on the wire. And force can be into the page or, current can be into the page or can be out of the page. Now I'm going to locate a wire, and this wire will have a current into the page or out of the page. You can choose any of them. So I will give into the page if electric current is into the page. This wire, when it carries a current, also produces the magnetic field around in section 2. Learn that. So magnetic field around the wires found by right hand rule, remember. For the thumb shows the direction of the electric current. Curved forefinger is the magnetic field around this wire, which is going to be clockwise fashion. So I will draw the magnetic field lines around this wire by circles. You know, they are concentric circles. One circle is this. Let me draw one more circle. It's enough. Two circles. There are more, but it's enough for my understanding. Because these circles are clockwise fashion. So, thumb is into the page, forefinger is clockwise fashion, like this. Now I want you to check the magnetic field directions above and below the wire. Above the wire, look at the direction of these magnetic fields. And magnetic field direction for the magnets and magnetic field direction for the wire. Are they in the same direction?
No.
Black and red, yes, they're in the same direction. So if the magnetic fields are in the same direction, resultant magnetic field gets bigger, huh? So above the wire, there is a region of stronger magnetic field. Stronger magnetic field. But look at the below the wire. Below the wire. So one of them is to the right for the permanent magnet to the right, the other one is to the left. So you see that their directions are opposite? If the magnetic fields are opposite in direction, so then they weaken each other. Now in here we have a weaker magnetic field. Weaker magnetic field. Okay? So above the wire, stronger magnetic field. Below the wire, weaker magnetic field. It is similar to this. Assume that in atmosphere there is a region of high pressure and a region of low pressure. Molecules of the air starts moving from high to low pressure, and wind occurs this way. Instead of pressure, high pressure and low pressure, we have in here stronger magnetic field above, weaker magnetic field below. This stronger magnetic field pushes this wire towards the weaker part. So where is weaker? Below. That's why this wire will experience a force from stronger magnetic field to weaker. So it's going to be down to the board. So down to the board, there will be a magnetic force acting on this wire. In which direction? From stronger to weaker. This is going to be the magnetic force acting on the conductor. Always, stronger magnetic field pushes the conductor towards weaker one. So strong is above, weaker is below. That's why magnetic field must be from above to below, and downward to the pitch. But what we observe in here is this. How many magnetic fields are there in here? Two magnetic fields. One magnetic field is because of the permanent magnet. Second magnetic field is because of straight wire. Which means, if you want to observe a magnetic force, you should have at least two magnetic fields. At least two magnetic fields. Then these two magnetic fields interact, and it is possible there to be a magnetic force. A single magnetic field cannot do anything. You need at least two magnetic fields. Right here, one magnetic field is the magnet's magnetic field. Second magnetic field is wire's magnetic field. And these two magnetic fields interact, and you observe a force because of the interaction of these two magnetic fields. Okay, keep this in your mind. This is not explained in this way in your book. That's why you don't need to know it or write it, okay? Just know what it means. Now I'm going to apply this principle to that title. That's why I explained that. So, to understand this title very well, we need to know what this is. Yes, summary. If you want to observe a magnetic force, you need at least two magnetic fields. Yani, wire magnetic field needs another magnetic field to experience a force. Okay, now I will continue now the title, this title. There are two currents. One current is wire 1 going up to the plane of the board. Second current belongs to the wire 2, again up to the board. Wire 1 produce a magnetic field around?
Yeah.
First magnetic field. Wire 2 produce a magnetic field around? Second magnetic field. How many magnetic fields are there? Two. If there are two magnetic fields, is it possible there can be a magnetic force? Yes. If there are two magnetic fields, one close in one another, so it's possible a magnetic force. That's why these two wires will experience a magnetic force. Magnetic force. Okay, if two wires carry currents in the same direction, first one, look at the direction of the electric currents. For the first wire, it is up to the board. For the second one, up to the board. They are parallel and in the same directions. If currents are in the same directions, these two wires attract one another. Yani first wire attracts second one attracts first. So there will be an attraction between these two wires. So these two wires attract each other with a force equal in magnitude. And their values are same. 10, 10, 20, 20, 15, 15, same. Opposite in directions. Are the opposite in directions? Yes, one of them is to the right, the other one is to the left. Third, act on different wires. Are they on different wires?
Yes.
One of them is on the first wire, second one is on the second wire. This is property of action-reaction forces. Action-reaction forces are always equal in magnitude, opposite in direction, and act on different objects. Yes, these two forces are action-reaction forces. They are equal in magnitude, opposite in direction, and act on different wires. So this is Mr. Exam question. If two wires attract one another, A, their currents are in the same direction. B, their currents are in the opposite direction. C, they are perpendicular to one another. D, none of them.
Yes.
So same direction. If electric currents are in the same direction, so these two wires parallel wire will attract each other. What if electric currents are opposite direction? What if electric currents are opposite direction? They will repel each other. So if two wires carry currents in opposite direction, these two wires will repel each other. Okay, can you predict the direction of the force if they repel each other? So this one repels that one. To repel, it must be to the right. This one repels the first one. It must be to the left. So their force directions will be right and left. Okay. These two wires repel each other if the currents are opposite. This is the important part as a ministry. If currents are opposite, wires will repel each other. If the currents are in the same direction, they will attract each other. Again, these two forces are equal in magnitudes. 10, 10, 20, 20, 15, 15, same. And opposite in directions, yes, to the right, to the left. And also acts on different wires. One of them is on the first wire, the other one is on the second wire. So they are also action-reaction pairs. So this is the part you have to absolutely know for the perspective of 12 grades. But now I will talk about how and why these two wires attract or repel each other. Okay. We know that each current carrying wire produces magnetic field around, circular magnetic field. I draw two wires. They carry electric current in the same direction. One of them I draw blue, the other one I draw red. Okay, now let's check the magnetic field around I2. Okay, electric current direction, thumb, up to the board. Curled forefinger. On the right, into, on the left, out. So this manner. On the right, cross, on the left, that. For red wire, electric current is up to the board. Again, on the right, into the page, on the left, out. These are magnetic field lines formed around these wires. What if I put these wires side by side? Yeah, let's put them side by side. Just like this. How many magnetic fields are there? Two magnetic fields. If there are two magnetic fields, is it possible there can be a magnetic force on each one? Yes. Now, be careful. Between these two wires, magnetic fields are opposite directions. Yani weaker. This region is a magnetic field, weaker magnetic field. Okay, look at that. Both are that, huh? Which means they are in the same. So stronger magnetic field. Stronger magnetic field. Weaker magnetic field. In here? Even stronger because cross. Stronger. Remember that. If there's a difference in magnetic field around wire, so there's a magnetic force. From stronger to weaker. This stronger part pushes this wire towards weaker. That's why this wire will be pushed to the right. But look at that one. Where is stronger part? On the right. Where is weaker part? On the left. This wire is pushed to the right. As you see, they are attracting each other. They're attracting each other. That's why their directions are like this. Reason is that these two magnetic fields interact, produces different intense of the magnetic field around, between them weaker, beyond them stronger. Stronger, weaker, stronger. Stronger magnetic field pushes a wire to the left. This stronger magnetic field on the left pushes the wire to the right. That's why these two wires attract one another. So, but one thing we have to know is this. I told you that each current needs a magnetic field, external magnetic field to experience a force. Look at here. Blue wire is inside the magnetic field of red one. Red wire is inside the magnetic field of blue one. Yeah, they are using magnetic field of one another. Blue is using the red one's magnetic field. Red is using blue wire's magnetic field. So, magnetic field of the red is external magnetic field for blue. Magnetic field of the blue is external magnetic field for red. They are using one another's magnetic field, so by this way they experience magnetic force. So each wire inside the magnetic field of the other, does each wire experience a magnetic force due to the magnetic field of the other wire. So now let's study them one by one.
So teacher, when the current is inside its own magnetic field,
No,
there is
no, hiç olmaz. A wire cannot produce a force by its own magnetic field. It needs something else magnetic field. It can be a magnet or it can be another wire. See that? This is blue wire. Blue wire produces its own magnetic field. How many magnetic fields are there?
one.
One magnetic field can push and pull another? No. So we need another magnetic field or another wire. Let's say that we are going to put another wire, red wire, inside this magnetic field. Let's put it. So a red wire we put inside the magnetic field of the blue wire. So according to right-hand rule, we can find the direction of the magnetic force acting on this blue wire. What is the magnetic field at the location of our first wire, red wire? Dot. What does dot mean? And this wire produces a magnetic field near dot. This is the forefinger is dot out of the board. Electric current of the first wire is up to the board. Look at my palm. What's the direction of the force? To the right. Left or right? Left to the right. Yes. It's going to be to the right. Yes. Yeah, this force, this wire, wire 1, will experience a force because of the magnetic field of wire 2. Yani red wire experiences a magnetic force because of the magnetic field of blue wire. So then let's continue. Due to the magnetic field of the blue wire, wire 2, wire 1 experience a force. A magnetic force acts on wire 1. Okay, at the location of the wire 1, what is the direction of the magnetic field of wire 2? It is dot. Magnetic field is dot. I wrote this B2, why? Because it's because of I2. So I2 produces this magnetic field. Second wire produces this magnetic field. So B2 is the magnetic field inside which there is the wire 1. Okay? A magnetic force acts on the wire 1. So what is electric current of wire 1? It's going to be I1. Magnetic field of the wire 1 is going to be I1. What is length of the wire 1? L1. There is a magnetic force according to equation. What is the equation of magnetic force? We know that. B-I-L. So force acting on the wire 1, say that it is F1. This F1 is going to be because of I1 and L1. However, magnetic field belongs to I2. So F1 is going to be B2, I1, L1. Let me repeat again. They are experiencing a magnetic force because of one another's magnetic field. First wire experiences a magnetic force because of the magnetic field of the second one. Second one, I2 produces a magnetic field in here, B2. This B2 causes a magnetic force on the first wire. That's why for magnetic force, I had to write here B2. So it's because of the second wire. Multiplied by first wire's electric current, multiplied by first wire's length. So equation for magnetic force is going to be B2 times I1 times L1. Now let's find the magnetic force because of I1 on the wire of I2. Now this is the magnetic field around this red wire. On the left it is out, on the right it is into. First wire produces a magnetic field around. Now red magnetic field produces its own magnetic field, and we put blue inside it. Blue is inside this magnetic field. Of course, so B1 is external magnetic field for I2. There's an external magnetic field B1. So if I want to find the force acting on this wire, my forefinger must point into the page because cross. Electric current on the wire 2 is up to the page. So look at my palm. It's pointing to the left. So this wire experiences a force to the left. Then let's continue. Due to the magnetic field of wire 1, because wire 1 produces B1 in here. Due to the magnetic field of wire 1, which is B1. On wire 2, which is B1. Wire 2 is acting a magnetic force. And on wire 2, there is a magnetic force. And this wire 2 has an electric current I2, length L2. So I2 and L2 is because of the second wire, but magnetic field is coming from first wire. Now when we multiply these three, yani B1, I2 and L2, I will calculate the force acting on the second wire, B1, I2, L2. I2 produces a magnetic field at the location of I1. I can get its direction. Because I1 is on the left my fingertips are showing out of the page. So this, let me draw by blue. I2 produces at the location of I1 magnetic field B2. Because of this B2, which is out of the page, but an electric current I1 up to the page. So this I1 is pulled to the right. So there's a force F1 because of the magnetic field of B2 on the wire of electric current I1, and length is L1. Similarly, I1 produces at the location of I2 an electric magnetic field. Let's find the magnetic field direction. So on the right, it is into. So it's going to be cross. Yani I1 produces here a magnetic field B1. Because of this B1, sorry. Look at the direction of electric current. Thumb. Look at forefinger on the right. Is it into?
Yes.
So into is cross. So B1 is into the page. Electric current I2 is up to the page. So magnetic force is to the left. Magnetic force is to the left. And this magnetic force F2 is because of the magnetic field of I1, yani B1, because of the electric current of wire 2, which is I2, and also length L2, yani B1, I2, L2. These two forces are action-reaction pairs. These two forces are action-reaction pairs. What does it mean? Their magnitudes are equal. They are equal to one another. F1 and F2 equal in magnitude. Okay. So now, about this title, there is a standard test prep question. Let's solve it, answer it. Okay. Standard test prep, use the diagram below. We are going to use this diagram now. This diagram, electric currents are opposite, not same direction. Remember, if two wires are in opposite direction, they will attract or repel each other. They will attract or, are they in the same direction?
No.
They are in opposite directions.
So they will repel.
They are in opposite directions. Now, not in the same direction. If they are in opposite directions, they will repel each other. So, if directly you can draw it. Yeah, this is going, force acting on this one is going to be like this. For one, that one is going to be like this. So, they will repel each other. This is say that F1. This is F2. So, question number 7. What is the direction of the magnetic field B1? What is the direction of the magnetic field B1? At the location of wire 2. Yani, I1 produces a magnetic field at the location of I2. Let's find its direction. What is the electric current direction of I1? Down to the page. So hold your pen so that your thumb must show direction of the electric current down. And curl your finger. On the left, into. But where is the wire? Is it on the left?
No, it's on the right.
So on the right. So curl it on the right. It is out. Yani B1 is going to be out of the page. This I1 produces a magnetic field at the location of wire 2, whose direction is out of the page. Look at this. Look at this. In or out? Out. Out yani that. Okay. So it is going to be out on the page. Question number 8. What is the direction of the force on wire 2 as the result of B1? Okay, now, for force we are going to open our hands like this. Forefinger is the magnetic field direction. What is external magnetic field in here?
Out of the
Dot. That is this. Out of the page. Look at the direction of the electric current. Is it up to the page? Up to the board? Yes. Thumb is up to the board. Look at my palm.
to the right.
To the right. Yeah, I already drew it. To the right. Because they repel each other. If they repel each other, it must be to the right. So to the right is the answer. And what is the magnitude of the magnetic force on wire 2? So wire 2. Now what's F2? What is F2? Questions about F2. Of course, it is equal to multiplication of B, I, and L. But B belongs to, of course, first wire. But I and L belongs to second wire. B1, I2, L2. Yeah, these are going to belong to the same wire, but this is going to be the other wire, first wire. B1, I2, L2.